So graphing tangent functions today. I'm going to start off with a graphing the cosine function. How about drawing a graph of the cosine function? So drawing this graph, what you want to do for this one is you need an understanding of what the 5 key reference points are for the cosine. That's what you sort of move up and down. So one of the points is here, where it starts off at 0, 1. It goes through here at 90 degrees. The minimum point is here at 180. Goes through the x-axis again at 270, and then up again at 360. So it's going to look like this. If you're drawing this one without, so if you're sketching it on a grid lines, then you need to be a little bit accurate with your grid lines. If you're sketching it without grid lines, it's a little bit easier and quicker. You can just put in some axes, draw the standard cosine function, label the points. I'll do it in radians this time. Sketching it only takes that long, so I sketch it. Even when you're doing the transformations, it's these 5 points that we're interested in. So the standard period for the cosine function, this is our period. Our period is 2 pi. The period for a trigonometric function is how long it takes for the function to repeat itself. How long it takes for the function to repeat itself. So the cosine and the sine function start to repeat themselves after 2 pi radians, or 360 degrees. Have a go at drawing the transformation of this one. Start by plotting the principal axis. Plot the translated position of figure out what the period is. Plot the translated position of the 5 key reference points, and then sketch the curve. All right, so let's start off by calculating the period. So it can be a little bit confusing. When I'm writing b here, typically I'm assuming that the standard form is cosine bx. But I know sometimes in the textbook we're using, they do cosine at 1 over b. So these little formulas would be, this formula I'm using here assumes we've got a cos or sine b bracket x minus c plus d. So this formula I'm using here is assuming the b is written like that. You will sometimes, we're doing it when we're looking at it, and we get 1 over b, and then obviously you've got to alter your formula when it's giving you this as the standard form.
When we're doing the IM3, it's like plus c, and it was like 3x plus c without brackets.
Yeah, it can be plus c. It depends on how you like to write it.
On the test, can we use the second formula and then we just write on the top that we would do the second?
No, but if you just write 1 over 2,
Yeah.
your b is 2 and my b is a half, and it will look the same when it's written down anyway. So
But I mean, like, when you're calculating the period, because then it would be period equals 2 pi b.
Yeah,
Yeah.
as long as the answer comes out right and I can follow it through, we get that.
So if you have the one like 4 with 1 over b, then the period is 2 pi b.
Yeah. All right, let's calculate the period.
Yeah.
So the period is going to be 2 pi over a half. So this is 4 pi. This is our period. Our vertical shift is going to be plus 1. So our principal axis is here. And then our vertical stretch is 3. So what would normally be 1 above the principal axis is now going to be 3 above the principal axis. We should cross the principal axis normally at pi over 2, but we've doubled our period, so we should be doubling that. So we're going to be crossing at pi. We would normally reach our minimum at pi. We're doubling that. So we should be reaching our minimum at 2 pi. We need to be 3 down from this, so 1, 2, 3 down from there, that's at -2. This one's going to be here, and then this one's going to be up here at 4. Let me just get that right. So our graph is going to look something like this. This one back in this direction is going to be there, and then maybe we've got one here at -2. I think we can get back to, oh, I missed that, that's slightly out, isn't it? It's at 4,4. And then that. So here we go. Our graph should look like this. It's important when you draw it that the bits going up from the principal axis are about the same size as the bits going down. That there's a lot of symmetry in it, and your shape should reflect that. Okay, next we're going to sketch tan x. So the tan function, if we think about the exact value table, I'll just pull up the exact value table for 0, pi over 6, pi over 4, pi over 3, pi over 2. And then tan x. So if we've memorized our exact value table, we've got 1 over root 3, we've got 1, we've got root 3, and then we've got undefined. It's this undefined part that is crucial to sketching the tan function. The undefined part is going to create a vertical asymptote. It's going to create a vertical asymptote. So the standard tan function has a vertical asymptote at pi over 2. It has another one at minus pi over 2. It's going to go through 0, 0. We can see that in the exact value table, and it's going to go through pi over 4, 1. So it's going to go through here. So this is 0, 0, and this is pi over 4, 1. It then gets reflected because in this particular quadrant, the sine value is negative while the cosine value is positive. So it's going to go through here at minus pi over 4, minus 1. And then it'll approach the asymptote. So the general shape for this looks like this. The function repeats itself between the two asymptotes. So the period for this is pi. The function will repeat itself at pi. The other functions all have a period of 2 pi. But for this one, we can see our period here. We can see the period here. And the period is pi radians, or 180 degrees. So the asymptotes will repeat themselves every pi. So 1, 2, 3, 4, 5, 6. It's going to go here. So that means if we want to continue sketching the curve, it's going to go through this point here. It's going to go through that point there. These are the 3 characteristic points. And then the curve continues. And then here, it's going to be coming down. Oh, sorry, let me just do the 1 point there. Get that one. Going to be coming down. This is how the tan function looks. So the important thing on this one is the period. The period is pi. The asymptotes occur at x equal to pi over 2 plus n pi. All of the asymptotes are at this particular point. Pi over 2 plus n pi. So crucial for sketching this one is to start by figuring out what your period is. Try and stay awake. Find out what your period is, and then find out how much your asymptote has been stretched from the original point. So look at the first one. Forget the period for a second. Look at the first one. Do we stretch this or do we compress it? Do we move it? And then you put all the subsequent ones different periods are possible. Once you've got those in place, it becomes quite easy to figure out what your 3 key reference points are and sketch it. Have a go at solving this problem now. All right. So first up for this one, find out what your period is. So the period is equal to the standard period over b. So it's not 2 pi over b, it's pi over b, because the standard period is pi. So b is equal to 3 over 2. So this is pi over 3 over 2, which is 2 pi over 3. This is our period. Now, because there's no horizontal shift, your period is 2 pi over 3, but it's evenly distributed either side of the origin, either side of the y-axis. So the 2 pi over 3, we cut that in half. Half of it, so let me just count 1, 2, 3, 4, 5, 6. We've got 6 of those, so this is pi over 3. Half of it needs to be here on the right-hand side of the y-axis. The other half needs to be here. That creates the asymptotes. They're evenly distributed either side without a horizontal movement of the y-axis. So they're here and here. This distance is pi over 3. This distance is pi over 3. Together, this distance is 2 pi over 3. Another technique I show. So I find out what the period is. The period is given by standard period over b, not 2 pi over b, or as I've been showing. But when it comes to tan, the standard period is not 2 pi, it's pi over b. So we put that in, we get the period to be 2 pi over 3. The period is going to be evenly distributed either side of the y-axis. So we just need to halve that. What's half of 2 pi over 3? We have 2 pi's over 3. Half that is 1 pi over 3. And we get pi over 3. Another technique that you can do is we need the function tan theta. We need theta to be pi over 4, 45 degrees. Sorry, no. No. We need theta to be pi over 2. We need theta to be pi over 2. That will create the non-defined part. We need it to be pi over 2. That will create non-defined. So whatever goes into here needs to produce a pi over 2. So if we want to produce pi over 2 from this function, we need this function to produce a pi over 2. So solving that, we get x is equal to pi over 3. And there's your asymptote. So 2 sort of strategies of how you can think to come to the solution there. You want theta to make a pi over 2 at 90 degrees, because the tan will then be not defined. So if theta needs to be pi over 2, this thing inside the bracket needs to produce that. Even if there's a c in there, you can put the whole expression in and solve. This will give you pi over 3, and there's your asymptote. The other bit's easy. We've got a vertical compress of a half. Now, the point that's normally at 45 degrees, comma 1, or pi over 4, comma 1, it's been halved, hasn't it? It's halfway between these two. It's halfway between these two. It's going to be here. Pi over 2 is halfway between the y-axis and the asymptote. So for this graph, it's halfway between. If this is pi over 3, this is pi over 6. So our point is going to be here, at pi over 6, comma a half. And our other point is going to be here. And we can sketch our curve. However, not quite right here on this one. Notice we're told there's a specific interval to use. So I can't include this bit. I have to start my curve here and show it going up. I do need to have a couple more asymptotes in though. So the asymptotes are 2 pi over 3 apart. So 2 pi over 3 apart. We just look at this face on. Our next one's going to be here. And then we're going to have one here. Okay, like this. So the curve is going to go through here. It's going to go through here, 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 here. It's going to finish there and go through here. So the graph that we need to draw is going to look like this. Notice in the question you told a specific interval to draw it. Now,
Is the point in the middle always in the middle? Like, kind of.
unless there's a vertical shift. We don't have a vertical shift here on this.
The other 2 points, is it always halfway between the points on
Yeah.
the, it's always halfway?
It's always halfway between the asymptotes.
Even if there's like a.
Yeah.
And
Whatever I'm messing you with, not where it crosses the x-axis, where it crosses the principal axis. The principal axis is the x-axis in this one because there's no plus d, but it's always halfway between on the principal axis.
like the other 2 points, like where, like the other 2 axes.
Yeah.
It's halfway between 0 and the asymptote.
It's between the points.
This point is always halfway between the asymptotes.
What about the other?
This point is always halfway between that point and that point.
And,
Yeah.
And what do the,
You can't sort of skew the shape. You can only stretch and compress.
and what do those points signify? Not the point of intersection, but the two on the.
They are in order to do a good sketch,
Yeah, that's
you can incorporate the vertical stretches and show the vertical stretch. Yeah, the three characteristics.
But
How high does it change? Like, let's say it's 2, what's the half?
that's what.
Well, if it's because the standard one is at 1.
Yeah.
So the tan function, no matter what's inside it, is going to produce at this particular point 1, and then times it by 8, and that's d.
But what do you change about the, okay, like the y of those integrals?
Not quite following, but let me try something.
Like, how do I change my vertical progression accurately in a sketch based on those 2 points?
Let's do a different one.
I told you it's not. But you can start the method, like, seems to be.
Should we try this one?
Like, I try?
Wait, there's no C?
Sorry.
And there's the same concept with the plus c and all that, they're the same assignment.
Similar.
So what does the 4 do?
You want to go straight?
Does it make a difference?
Yeah.
So if it's like 4, it'll be more interactive, and if it's like compressed,
Do we have to show it?
Yeah.
that's like my question, like,
How?
where, like, yeah, what does.
So typically, as opposed to... Sorry, I'm going to pause the video. Okay, let's redo this one. So our period. What is the period going to be? Period is pi over a third. So 3 pi. Half of the period is 3 pi over 2. So our asymptote is going to be here at 3 pi over 2. Oh, sorry, it's not good. 3 pi over 2. There. Our other asymptote will be minus 3 pi over 2. I can't quite fit that one in. Sorry. Our Principal axis, we've added this in now. We've moved everything up by 1. So it's going to cross this line. It's going to cross this line here at this point. Halfway between 0 and 3 pi over 2 would be 3 pi over 4. Where's that? 3 pi over 4 would be about there, wouldn't it? That's halfway between. We've got a stretch of 4, so we're 4 up from the principal axis, so that would be up here at 5. So our curve is going to go shooting up like this. And here in this direction, it would be at -3/4, so that's about there. And then it would be 1, 2, 3, 4, 1, 2, 3, 4 down. It's going to look something like this. It's going to go through 3 pi over 4, comma 5. It's going to go through -3 pi over 4, comma, oh, I can't comma -3.
So how do you know that it's pi?
It's going to go through 0, comma 1. And our asymptotes are at 3 pi over 2 plus n 3 pi. Sorry, let's have a go at this next one. I need to push on a bit now. Let's have a go at this question now. Now, I'm going to start with my formula for the period. I'm going to be using the formula A tan Bx. I always use this form, and then I'll put it into the form that the question is asking me for. So for this, B is equal to pi over the period, which is there 1 over B. Annoying. So B is equal to this. The period is 1.
So how's it
Oh, yes, the period is 2. This is 1. The period is 2. So we've got pi over 2, which is B. The stretch, we can see the stretch here. They've stretched it by doubling it. So they want f of x is equal to 2 tan 2x over pi.
No. That's wrong.
Yeah, you're right. I'm so smart.
Yeah.
I did it.
I went to Europe. Europe.
Yeah, remember how we said that it's originally the y?
No.
Yes.
Exactly.
Because it also could be different when it's plus 1.
I told you, Alec's always right. So, writing it in my form, I get pi over 2x. So this is the correct function. This is the correct function. This implies that the b given here, so this is equal to 2 tan of 2 over pi 1x.
Which is the same thing as pi over 2. It's not 2 over pi, that's wrong.
So their b, which isn't the same as my b, because they're added 1 over b, so b always creates a value of bigger than 1 always creates a stretch. It's 2 over pi.
1 over b is 2.
I'm gonna skip a little bit to the modeling question.
So can you go back? On your side.
So what's our next major?
something like the 2nd of May. Look on the
What?
calendar.
Is it one?
Sorry, no.
What's the
No,
other
no.
Wait, sir.
Sir, I have a science major in
No way.
Wait, what?
Sir, it's the 24th. Sir, I know.
Next week.
Have to do. Let's have a look at our modeling question. A climber is ascending the face of a 500 high vertical cliff at 5 feet per minute. So if we wanted to define his height, we could say that his height is the function of time. What would be the function that defines his height at any given point in time?
500 minus 5t.
No,
500.
he's climbing up, not down.
Or 5t. 5t.
So this is 5t.
Between 0 and 500.
How long can he climb for?
100.
100.
Or 100 minutes.
It's 102.
So
in what? Minutes?
Why? Sorry, what's the sentence?
Going up.
Right.
So this is his
Yeah.
height. That's the first bit. Her climbing partner is observing from 150 meters away. Let's draw a little sketch of this problem.
Is it down or up?
It's going up.
Yeah, but is the climbing partner above him or below?
Below him.
No, it's just away.
Why would the climbing partner be standing at the top of the cliff observing at 150 meters away, sort of floating like Avatar or something? Very odd. Okay, so our distances. The maximum here is up to 500. Here's our climber. They're climbing up. The observer is over here at 150 meters away, and then she's observing him like this. And the angle here is changing. This is the angle theta. That one's going up slightly, like this.
The guy's climbing.
That's the first step. That's angle diffusion.
The guy is climbing in this direction
Right.
from the bottom, and we'll stop here. This person is standing, it says here, climbing partner is observing from 150 meters away. So observing from over here, looking up.
150 feet from the wall or the person? Probably the person.
So you're watching the person.
As he comes up.
Okay.
Oh, I thought he was there, like behind him, 100 feet away, 100 feet away, always behind him.
Observing. Find the function that describes the amount of time climbing as a function of the angle of elevation. So the relationship between this length and this length is given by trigonometry. This would be the opposite. This would be the adjacent. And we can say that the tan of theta is equal to the opposite over the adjacent. So we want to find out the adjacent is the distance she's standing away. So we've got tan theta is equal to the opposite over 150. Now the opposite is the height. That's the height, which is h of t. So tan theta is equal to 5t over 150. And then we need to rearrange this and make a function of t is equal to 30 tan theta. So there's our function. Find a function that describes the amount of time, so the amount of time of climbing as a function of the angle of elevation. We need to put in a domain for this function. So in order to find the domain, theta is going to start off at 0, and it's going to go up to a maximum when the height is 500. So if the height is 500, the opposite is 500. We can find this on the calculator. We need to do, not that one, trigonometry. Let's focus on solving this problem here today. Arctan of 500 over 150. Okay, so there's a simple value for you. I'm in degrees, 73.3. So this goes up to 73.3 degrees.
Why did you divide?
Also, yeah.
Oh, so
So why did you do it?
So Does the viewing angle ever reach 75 degrees? No, that's outside the
What if
domain.
it jumps?
With the nose.
I think give him a F just for that stupid question. That's 500 dollars. And just 150. Mine's
Your problem for the high problem, you can have a ladder against the wall or a zip line.
How many major survivors?
And we have had, and we have science semester in June. No, it's major. We have science major.
I know, sir. What's 30 is 30 first? Math next week. Also, what else next week? Oral history TBQ is on May 2nd. Fine, it's May 2nd to the.
That's the day after the
My English major is due on Friday. Like the last 2 months are always the hardest. Because I know I just have to like push through, but it's too hard. It's hard. It's like I think I'm gonna get like an A on my science. I think I'll do good then.
Why are you being next?
Absolute horror, terror, and worry on my face right now. That I
IM3.
English majors want Sunday.
No, you don't.
Yeah, we do, sir.
No, you don't.
It's a project, sir, it's a project. Yeah, so we have a five.
Projects have to be on here too.
No, but they didn't.
Why is there not a schedule? Sir, we have a
Because
five videos due on Sunday.